Now let's have a look at how these few modifications actually improve the performance of the code a lot. So let's place our start point here and our end point here in the opposite direction, as we did earlier, and we can see that it comes up immediately with a solution. And as we move this point closer, it does the same thing as it did earlier. So it works quite well. So now let's test this critical case where a relatively long trajectory is combined with different orientations of the start and end nodes. Now first, the orientations of the start node are again handled pretty well. And now the orientation of the end node takes a bit longer, but it's also handled very well. So let's have a look at the visited nodes. So again, it visits only a few nodes in this case, and if the orientation is wrong, it visits more nodes, but still much less nodes than it visited earlier. Now let's make some practical examples. Say we are in a parking garage and we backed up into this parking lot. So this is the parking lot in between those lines. But actually we want to go into this next parking lot. And so the planner makes a left turn and then a right turn with the minimum radius it can do, and then goes into this parking lot. So here is the bounds of the other parking lots. Well, unfortunately, on the opposite side, there is parking lots as well. So the planner comes up with a solution to make the turn up here. If there's another parking lot, it actually goes around. Well, this might not be possible because here there might be a back wall. So it goes up here and does the turn up there. Now, this may be the end of the park deck here, so here might be a wall. And so it goes around the structure somehow, but well, this might be not possible as well because there is a wall here, so it goes around the entire thing. Now, this may be also not possible because there's a wall here. So the planner searches for some empty space where it can turn the vehicle. Now, if there is a narrow passage down here, it will go down here and do here the circle with minimum radius. If this is not possible, it will try to search this minimum radius somewhere else. So it's pretty cool watching the planner find alternative solutions like this one, which is of course also not possible if this wall blocks this maneuver. Now, of course, if there is no space whatsoever to make your turn, then the planner can't do anything. Right? It visits all those nodes, but it can't do the curve because there's simply no space. However, if you allow forward and backward motion, it will do something that makes really sense. It will go out forward to the right, back up a little bit, and then go into the parking lot by a forward movement. And if this somehow changes its shape, then you will see how it will try to do other maneuvers. Or if there's a car, it will try this one. So if you switch on the visited nodes now, you will see of course that the forward-backward solution is much more efficient than the forward-only solution, which has to visit a lot of nodes. Now, this is too narrow, in order to come up with a feasible solution. So congratulations if you made it through here. I think by now you have learned a lot about Dijkstra's algorithm, the A-star algorithm, and finally our kinematic state space algorithm, which finds paths that can actually be driven by a real car. So again, congratulations, and this finishes this part of the lecture.